Telling us about some harmonic analysis techniques in complex variables. So thank you very much.
Thank you very much for the lovely introduction. I'm very happy to be here, and I knew this was a great department for many reasons, but getting to meet you in person adds another dimension to the experience and my perception. The topic that I've chosen for this lecture is actually something that I've been working on recently. And so I thought, since you are interested in knowing me and my interests and my work, that maybe it would be a good idea to give you first a very brief outline of the work that I've been doing prior to this, to sort of give you a better sense of what I've been working on over the years and what I'm interested in. And then I will switch to the specific topic. So for those of you who haven't met me or do not know me, I'm an analyst. I work in the area of analysis, and my research interests interface with various subfields. In particular, I work in harmonic analysis and elliptic linear PDE, several complex variables, geometric function theory. Operator theory is more of a means than an end for me, but I use tools from operator theory. The emphasis of what I do is typically on rough setting. That is to say, you work on ambient domains that are allowed to have corners, are allowed to have spiral cuts, in fact infinitely many spiraling cuts, or are allowed to have cusps. So this is the kind of setting that I work with. The general philosophy is, whenever possible, to sort of bring together ideas from these different subfields for mutual benefit. And if there was to be one common theme that I have to pick up, it would have to be the use of integral kernel-based representation formulas, as you will see. So in chronological order, I've been working on problems dealing with complex function theory for rough, in the sense described above, planar domains, by combining techniques from conformal mapping, the Riemann mapping theorem in one variable, with the theory of Calderon and Zygmunt for singular integral operators. I've also been working on boundary value problems for elliptic operators on Lipschitz domains, combinations of Neumann and Dirichlet conditions, or the mixed boundary condition, where you allow Neumann on one piece and Dirichlet on another. More recently, I've been interested in problems that are, the terminology here is borrowed from the engineers that live in three dimensions, divergence and curl. But actually this is stuff that works in any dimension. So divergence and curl inequalities, duality estimates for a number of differential complexes acting on Euclidean space. Originally the complex would be exterior derivative, the differential operator. Higher version of that. And more recently, and this last project is ongoing with Paul and Young, we've been looking at conformally invariant versions of these differential conditions, especially pertaining to the covariant derivative. And so we've been working with Witten complex on certain Riemannian manifolds. And that's that. As I was saying earlier on, more recently, I have become interested in building a large part of this project within the context of several complex variables where there is new twist that's added. And that's the complex structure that one has to contend to deal with. And so from now on, I'll focus on the specific topic of this talk. And I will talk about joint work with Dave Barrett and Eli Stein in particular, and I will provide references at the end for those of you who might be interested. So the motivation for all that we have been doing is actually very classical. It's the Cauchy integral as we teach it in first year introductory complex analysis courses. In fact, this is exactly what I was doing yesterday at this time in Arkansas. So this is the Cauchy integral as I was explaining to my students yesterday. And that means you're dealing with a domain in the plane. This would be our domain here. You're integrating on the boundary of the domain. Here is W. And you're evaluating at a point which is inside the domain. However, from the point of view of harmonic analysis, this is not enough. In other words, you want to allow for the evaluation point Z to actually also be on the boundary. And once you allow that, then W at some point will be equal to Z, and so this denominator becomes problematic. And so what you're dealing with is what people call a singular integral operator now. It's a singular integral. And one way of dealing with that is to bite off a piece of the boundary, an epsilon piece of the boundary. So take this away, disregard it, and integrate only on what's left outside. So once you do that, Z and W are no longer allowed to be equal. And so the integrand is well defined again, and the output will be something that does depend on your epsilon. And so what you want to do then is let epsilon go to 0, cross your fingers hoping that some convergence will happen, and this is exactly what happens for the Cauchy integral. And you call that limit the principal value. So these are the kind of singular integrals that I'm interested in. The reference result is the study that was initiated by Calderon and then Koifman, McIntosh, and Maillet a few years later of that particular kind of integral operator in the plane, in the situation where the boundary that you're looking at is the boundary of a Lipschitz curve. So it's something that is allowed to have corners, so to speak. And it's locally parameterized as the graph of a Lipschitz function. The number m tells you something about the size of the largest corner you can wedge in. So why is that particular kind of curve, interesting? And why was it a watershed moment in harmonic analysis when they were able to study this operator? So the problem is to study the regularity of the integral as a singular integral operator acting on Lebesgue space, the space of functions that are differentiable, whose Pete power is integrable on the boundary. The reason why Lipschitz was so crucial is because if you look at the kernel function, which we had in the previous slide, and now you think of your W and Z as point on this curve, so W will correspond to a value of T, Z will correspond to a value of S. And if you assume for a moment that A is a smooth function, so that you can develop it, do a Taylor expansion of order 2, say, and then because you're dealing with 1 over that, you actually apply partial fractions. So in the end, if you do all of that expanding A, what you get is an expression that looks like this. Now, S and T are real numbers. So what you have here is actually a classical object of harmonic analysis. The first ever singular integral to be studied is the Hilbert transform that people know very well, completely well. Depending on how good or how bad your A is, you may or may not have problems controlling the remainder. It turns out that if the curve is pretty good, for example, A is differentiable once with a continuous derivative, C1, then this remainder is already a little bit hard to deal with. In other words, it's not a trivial perturbation of the Hilbert transform. And you have to do some work that was done by Faves, Jodite, and Riviere in the mid-70s, but you can still reduce everything to the study of the Hilbert transform. On the other hand, as soon as the boundary is Lipschitz, as soon as your A is Lipschitz, this remainder becomes intractable with the techniques that were available at the time. And so new ideas and techniques have to be developed. There's also a higher, the reason why we have two sets of people that are being attributed to these results has to do with M. You need to have different techniques depending whether M is a small number or a large number, and they separately took care of that. Koifman, McIntosh, and Maillet also had a higher dimensional version of this result for an operator that's known as the double-layered potential operator. I will not give formulas here, but I'll say about the role it played in later developments. So, once the LP regularity of the Cauchy integral for a Lipschitz curve was established, that started off the renaissance of harmonic analysis for the past 40 years. And in fact, this result has had a very long-standing impact. For instance, in elliptic linear PDEs, in particular the study of boundary value problems on Lipschitz domains. That's the double layer potential operator I was referring to earlier on. In fact, new techniques for the study of singular integral operators were developed as a result of the techniques that were introduced to prove that original theorem for the Cauchy integral on a Lipschitz curve. Further applications that are going on to this day to geometric function theory, the study of analytic capacity, removability of compact subsets for analytic functions. What I'll be focusing on later on, time permitting, would be applications to several complex analysis in one and several variables, in particular the study of orthogonal projections. So on the basis of all of this, we set it as our goal to see what can be done in order to extend the theory of the Cauchy integral for a Lipschitz curve from one dimension, from one complex dimension, the plane, to several dimensions, the Euclidean complex space Cn. So you see, the first task you have to give yourself then is to find a higher dimensional analog of this kernel. If W and Z are complex numbers, this expression makes sense. But if W and Z are complex vectors, 1 over a vector no longer makes sense as written. Okay, so that's already something you have to cope with. And it turns out that you get a pretty good idea by, again, the first year complex analysis course, because something that one learns there is that an alternate expression for this object is in terms of complex conjugates. Okay, that's maybe better. So if W is x plus iy, W conjugate would be x minus iy. And it's easy to check that these two objects simplify down to that. The absolute value squared is precisely the product of the object times its conjugate. And now this is promising, because this is an expression that does make sense also in higher dimension. And so if you exploit that, oh, and by the way, here we're trying to carry on the Calderon type program, right? So we're looking for kernels, and we're also looking to study them on boundaries that have, in some sense, minimum regularity, and we look at the same kind of problems that they did back then. So if you implement this one-dimensional trick in higher dimension, the operator that you're actually working with is the Buckner-Martinelli kernel. Notice that when I talk about kernels here, I don't just think of a function, but rather I think of a differential form. And the form has the same degree as the dimension of the boundary that you're working with. So in the plane you have d omega over omega minus z, because the boundary is one-dimensional. Here you have a form of degree 2n minus 1. So what are the good news about the Buckner-Martinelli kernel, which has been around for, I don't know, since the 1940s, for a while? The good news is that indeed this is a higher dimensional generalization of the Cauchy kernel. If you let n be equal to 1 up there, everything simplifies down to the original kernel. The other piece of good news is that if you study this kernel as a singular integral operator acting on the boundary of the Lipschitz hypersurface, again, this operator is bounded in LP. And this is thanks to the Koifman, McIntosh, and Meyer result concerning the double-layered potential operator. Because if you break this quantity here, this expression, into real and imaginary parts, and then you restrict it to the boundary so that this becomes surface measure, you get a combination of two kernels, one of which is actually the double-layered potential, and the other is a related operator, essentially the tangential gradient of the single layer. Those who are familiar with that. And both operators have been studied by Kaufman, McIntosh, and May, and the answer is positive. Another good property of the Buckner-Martinelli kernel, it satisfies a Cauchy formula. Cauchy formula means that if you start with a data f that is analytic inside the domain and continues up to the boundary, and then you compute the Cauchy integral, the Buckner-Martinelli integral of f at an interior point z, you recover the value of f at z. Okay, so this operator has this property as well. But there are also bad news. which are good news for me and my collaborators. And the bad news are as follows. You see, this function, again, here we're thinking of z inside and w on the boundary for the time being. So this is a function that for each fixed w is analytic in z. This isn't obviously analytic in z because you have a dependence on the conjugate up here and you have an absolute value square down here. Okay. But things simplify down, and it turns out it is analytic. The problem with higher dimension is that you can no longer effect that simplification. Up here, you only have one component, L. Here you have the entire absolute value to the power 2n. So you cannot simplify. Bottom line is, the coefficients of this kernel fail to be analytic. In higher dimension, people say holomorphic. And this has very bad consequences as far as the applicability of this operator to the study of specific objects in complex analysis, orthogonal projections, or Bergman projections. So, you have a problem. And the problem translates into imposing a further constraint in the problem you're trying to study. Not only you're now looking for a kernel, but you're looking for one that happens to be analytic as a function of z. And Bach and Martinelli is not. So as soon as you put in this new constraint of analyticity, interesting things happen. And the interesting things happen is that there are new requirements on the domain that pop out, both on the geometry of the domain and on the amount of regularity that you can allow. In particular, the domain has to have some kind of convexity, which of course didn't happen in dimension 1. So let's try to figure out where that comes from. The problem is that as soon as you require holomorphicity, you have these new constraints that come out, which are induced by the dimension, these obstructions, the fact that you're working with several as opposed to one complex variable, and also obstructions that arise from the complex structure that you're looking at. In other words, you're not working with 2n many real variables. You're working with n complex variables. There's an imaginary unit and multiplication by it that plays a role. And it is these obstructions that lead to the requirement that the domain you're working with be pseudo-convex. More about this later. I'll just say now that in dimension 1, pseudo-convexity is an invisible phenomenon. Every domain is pseudo-convex. And now, so this is a dimension in this phenomenon, but it's something that in a different context we're all familiar with. If you think of the regular convexity notion, the statement that every connected open set in a space X is convex, well, this is a statement that is true if the space is the real line. Connected open sets of the real line are intervals. But it's false in dimension 2. Take an annulus. Okay, so this is a kind of phenomenon that we are familiar with in a different context. But I haven't told you yet, really, why this requirement of holomorphicity makes this phenomenon pop out of pseudo-convexity. Let's see if we can make sense of that. See, the problem is that when you look for a kernel that's analytic or holomorphic in Z, or fixed W on the boundary, what you're really looking for is a function that's holomorphic in Z and is singular, cannot be extended analytically past W. Now, in dimension 1, you can always do that. You give me a W, I give you an f of Z which cannot be extended past W. Here it is. And it's not a coincidence that the function that you can use is the Cauchy kernel. Okay? On the other hand, in dimension 2 or higher, complex dimension 2 or higher, there are indeed examples of domains for which this may not be the case. In other words, you can have points in the boundary such that there is a neighborhood of that point with the property that any function that's analytic in the domain can be extended analytically past that point. It's the discovery of this phenomenon in the early 1900s, 1910, by Hartens, that marked the birth of several complex variables as a subject in its own right. So let me give you an example of a bad domain. And of course here we have to be in at least two complex variables, so we have to come up with tricks for drawing pictures. And the trick here is to look at the absolute value space as opposed to the entire space. So a point here is not going to be a point, it's actually the product of two circles, it's a torus. So with that in mind, Hartog's example looked like this. So the domain D0 that he came up with was this. And the remarkable phenomenon that he discovered was...
So you mean all points that have those absolute values?
Yes.
Okay. All
Right.
points
All points with absolute values falls into this picture. So the phenomenon that he discovered is that if you pick a boundary point that happens to, whose absolute value happens to be here, then, and you take a function f that's analytic in the shaded area, then you can automatically always extend it analytically through the product of these two disks. So there is no way of finding a holomorphic kernel with a W in here that's not extendable past W. So like I said, this was a watershed moment for complex analysis. This is when people realized that they were dealing with a new field back in the early 1900s. So this is the enemy. So now, what is the Levy problem? The Levy problem is exactly the problem of characterizing what are the good domains, domains for which this phenomenon cannot happen. It took people about 40 years to solve this problem, and Oka was one of the major contributors in the 1950s. And it turns out that this is a problem that doesn't have to do with analysis. It's a problem that has to do with geometry, the geometry of the domain. So guaranteeing the existence of a bad function, one that you cannot extend holomorphically past the boundary, is equivalent to the domain in pseudo-convex. So people have written books about different notions of pseudo-convexity, Hormander being one of them. I'm not going to discuss most of these notions, I'll discuss just one. But I want to give you later on, but I want to give you a sense of what kind of results had been known for a long time. So the first result is due to Kurzman and Stein for this part, and Henking and Ramirez for this part. It goes back to the same time when Calderon was studying the Cauchy integral and Lipschitz curve, by the way. But what they were working with, instead of Lipschitz domains, were very smooth domains. Domains that allow for at least 3 continuous derivatives in the functions that define them. And they were using one of the many notions of pseudo-convexity that pertained to the Levy problem. So for this notion of pseudo-convexity, they were able to construct a holomorphic kernel via an algebraic procedure that goes by the name of Cauchy-Fantafi. The deal with that is anytime you deal with pseudo-convexity, good things happen, but they only happen locally. So they were able to find a function, a kernel that was locally holomorphic for Z near W. And that was the whole affair, which I want to discuss here, of making it into a globally holomorphic kernel. For those that are familiar with this field, that was the solution of a D-bar problem, but I'll say no more. Anyway, they were able to construct a globally holomorphic kernel for this kind of domains. Kurzman and Stein were able to prove the regularity of the corresponding integral operator. Their method was interesting, and it worked like this. They looked at a spatial domain, the Siegel upper half space, which, as you can see, is a very smooth domain, is defined by way of a polynomial. It turns out that for this particular domain, writing down the kernel is very simple. And showing that the corresponding operator for this domain is a relatively straightforward affair. You can do it by hand. The trick was that if you deal with a strongly Levy pseudo-convex domain, at every point in the boundary of this domain, you can actually osculate it with a copy of the Siegel upper half space. You have a very good tangency, up to order 2. Not only that, if the domain has at least 3 continuous derivatives, the error that you make in going from the integral operator for the original domain to the integral operator for the model domain is negligible. And so you can transfer the regularity. It took us 35 years to reduce the assumptions of the original result by 1 unit. The problem was not so much with the construction of the kernel, though there were some technical abstractions which I won't discuss. The problem was primarily with the method of proof of LP regularity. If you try to go with the osculating by model domain approach again, you still have the oscillation by the model domain. The problem is that with only 2 continuous derivatives, you can no longer control the error in going from the model operator to the original operator. So the method doesn't work anymore. New technology is needed. I will get back to that later, but here I want to discuss our most recent result, which deals with another notion of pseudo-convexity, which one can actually describe by drawing a picture. And so the particular setting of interest here is the setting of a domain that's strongly linearly convex, and whose boundaries regularity has been further reduced to C11. C11 means the following. You can describe your domain as the set of negativity for a function defined in entire space. Boundary is the set of points where the function vanishes. And the assumption of this function is that it has one continuous, its gradient is continuously different. The function is continuously differentiable. And in fact, it's a little better than that. The gradient is Lipschitz, better than continuous. Okay, so the components will have, if you graph them, so what is the kind of convexity that we work with? It can be described as follows. So this is our domain. Here is a generic point in the boundary domain. You look at the real tangent space at that point. That's a space that has real dimension 2n minus 1. Well, it contains a special subspace. The special subspace, as I will picture like this, is a subspace that has dimension 2n minus 2, or complex dimension n minus 1, and has the following property. If you take a vector in this subspace, and you multiply it times the imaginary unit, you're rotating it, you get a new vector that's still in there. It's closed under multiplication by the imaginary unit. So that's known as the complex tangent space. Right? It has a complex structure of its own.
So it's a complex vector space.
Yes, as opposed to this one. So what is the property of being then strongly linearly convex? Property is the following. At any point in the boundary W, you can find a quadratic paraboloid whose opening does not depend on W. C is a fixed constant. And this quadratic paraboloid completely separates the original domain from the complex tangent space of W. And you can do that with a paraboloid having same opening, aperture, at any point W. It's a specific separation point property. Notice that the domain could intersect the real tangent space along the missing direction. That could happen. But not the complex tangent space. Our old friend, the Siegel upper half space, is an example of exactly this phenomenon. Here we're giving it in dimension 2. So this is an example of a domain that is strongly linearly convex. You'll have to take my word for that. But it's easy to see it is not strongly convex because the boundary contains a lot. So for this kind of domains, indeed it is possible to construct a kernel function, or rather a kernel form. And it looks like that. So this would be the analog of the Buckner-Martinelli kernel for this particular family of domains that we've been working with. And again, in the numerator, you have a differential form of degree 2n minus 1, just like you had for the Buckner-Martinelli kernel. Except now everything is defined in terms of a specific defining function for the domain. And the denominator is a pairing of complex vectors, which is not the Hermitian pairing. There's no typo here. There's no complex conjugate. So this particular kernel was first introduced by Jean Leray in the 1950s. At the time, he was working with smooth domains, C-infinity smooth domains. In fact, C2, two continuous derivatives are okay, and strongly convex. So a stronger notion of convexity than the one we're looking at. So let's see what are the good news about this kernel. First of all, you can write it down, and it doesn't take 5 lines, which is the case for the strongly pseudo-convex domains, which is I'm keeping away from. Now let's look at the situation that Leray was looking at. The domain has 2 continuous derivatives. This means that rho here is continuously differentiable twice. So the numerator makes sense. So the good news are that something I haven't told you before, you can find a lot of different functions rho that describe the same domain. Now this kernel is defined in terms of such a rho. In order to have something interesting, you want to have a kernel that doesn't depend on the choice of function that you're using to define it. And it turns out that whereas this whole object here does depend on the choice of rho, if you restrict it to the boundary by using the inclusion map, what you get actually does not depend on the choice of function. It's canonical. So that's good news. Also, the fact that the domain is strongly linearly convex translates analytically into saying that the denominator here doesn't vanish. So it's a well-defined kernel. Not only that, if you look at it as a function of z for fixed w, you see that the numerator doesn't depend on z. So what you actually have is a rational function of z. It's 1 over a polynomial. And this polynomial doesn't vanish by strong linear convexity. So this function is analytic, holomorphic. And you don't need, this is a global holomorphicity. It doesn't just happen when z is near w, as for the strongly pseudo-convex domain. It happens in the entire domain D. So no need for correction. Now let's look at our situation. In our situation, we're not assuming that the function has 2 continuous derivatives. We're only assuming that it has 1 continuous derivative and then Lipschitz second derivatives. So there is a classical theorem in harmonic analysis that studies the regularity of a Lipschitz function. Lipschitz functions can have corners, but this theorem tells you that they can't have too many corners. In fact, they're going to be differentiable almost everywhere, and that these derivatives will be in L infinity. They have some fixed control. We have fixed control on the decay. If you iterate the theorem once, and you look at C11 functions, then this is the corresponding statement for 2 derivatives. Now, what's the problem here? The problem is that this is a space that doesn't set C sets of 0 measure. And the problem with us is that the boundary, which is where we're integrating, actually has 0 measure. So there is no guarantee that what you have up here may actually be defined once you restrict it to the boundary. That was a concern. You may actually not have a kernel. And it turns out that you're okay. In fact, you do. And this is just a specific way of stating it. So this particular family of second-order derivatives, when restricted to the boundary, indeed exist almost everywhere on the boundary and have the kind of regularity that you would like them to have. Rademacher-type theorem. Notice that this statement is a little more general than what we need. Here, f is any C11 function. It doesn't need to be the defining function of your domain. Although you can decouple the domain from the function. Although in our applications, we'll be using f to do just the same. And from a computational point of view, to actually prove things, this existence result will not be enough. You actually need to manufacture in an ad hoc sequence of smooth functions that has the right convergence to the original data. And it is with this particular sequence, so here you would put a k, and then take limits. So it's using that particular sequence that you prove everything you need to prove. For example, the Cauchy formula.
That's why you needed the general form of the theorem, so that it gives the proof method.
Exactly. let's move on. We're not going to discuss the proof, but we'll discuss an example which is exactly the example that worried us for a long time before we actually managed to prove the proposition. The example is in the plane. We're in two real variables, one complex variable. And you look at the function of x and y given by just the absolute value of x. This is the typical example of a Lipschitz function that we show in Cal 1. And now, as your domain, you take, let me see, the left upper half space. Okay, x plus y can be anything you want, x is to be negative. So this is clearly a smooth domain, the boundary is a line. This function is obviously Lipschitz in the entire space, and so by Rademacher theorem, its gradient is another infinity. On the other hand, when you actually compute the gradient and you restrict it to the boundary this way, you realize that it's undefined. But then you look better, you look more closely, you look at both components of the gradient, the x derivative and the y derivative, and you realize that the only problem is with the x derivative. But the x derivative is precisely the normal direction, the normal derivative to our boundary. There's no problem with the y derivative, which happens to be the tangential derivative. And the proposition in the previous slide shows that this phenomenon is general for the kind of functions that we work with. Okay, so our initial goal was to find an analog of the one-dimensional Cauchy kernel, right? Let's see how far or how close we are to that. So if we take our kernel here, which is now well-defined in our context, and you restrict it to the situation when the complex dimension is 1, you have that n minus 1 is equal to 0, so it's like wedging with 1. And so that expression up there reduces to this in dimension 1. And if you compute it explicitly, obviously things simplify down to the original kernel. Not only that, if you now consider the situation of the Cauchy kernel for a Lipschitz curve, a la Calderon, written in this way, you see that what you have here is an object whose numerator is Lipschitz. Just like what you have up there, a Lipschitz coefficient, in the situation when the domain is C11. And so in this setting, we can say that the Cauchy-Leray kernel is the higher dimensional version in the context of the original kernel of Calderon for a Lipschitz curve. So those are the good news. Bad news, there are bad news, but you don't get to see them until you take a microscope. The microscope in this case means that you're not just looking at the Cauchy integral, but you're looking at the difference of the Cauchy integral and its adjoint, L2, formal L2 adjoint, which is something that's of interest in the applications. So this is a singular integral operator. That's also a singular integral operator. And the kernel is given in this way. Switch the variables, take a complex conjugate. Now what happens in one dimension, and this is a phenomenon that again was discovered by Kurzman and Stein, is that when you take these two kernels and you compute them for a curve that's sufficiently smooth, the bad part of this guy will cancel out with that. There will be a cancellation of singularities. And so the outcome kernel, which is coming from the difference of the two operators, will be much better than each of the two kernels taken separately. In fact, you get a compact operator. It turns out that if you try to look at the same procedure for the Cauchy-Leray kernel in higher dimension, you'll have this magic cancellation only under very special circumstances, even for smooth domains. Anyway, now that we have convinced ourselves that our operator is well-defined, and it is in some sense a reasonable higher dimensional analog of the one-dimensional Cauchy kernel, we can state the main result. The main result is in the spirit of Calderon and Kochman-Mackintosh-Meyer, with one twist. Those people were interested in looking at regularity with respect to Euclidean surface measure. Instead, we get regularity with respect to a measure that's given by actually the numerator of our kernel, what we call the Leray-Levy measure, for reasons that will be clear in a little while. As far as the technology, as we said, this osculation by model domain techniques doesn't work anymore in this context. Instead, we borrow a technique that was developed in real harmonic analysis starting from the 1980s and enjoying great developments to this day, what people call a T of 1 theorem technique. In the special setting when T of 1 is 0, T star of 1 is 0, which is a special situation I'll describe in a minute. And we have to do this not for Euclidean space, but rather for a space of homogeneous type that reflects the geometry of the boundary. The fact that we're doing with some kind of convexity. So for those of you who do not work in this field, a space of homogeneous type is a triple. A supporting set. On this set, you have a quasi-metric. This would be a metric if you had equality here, and if you had a less than or equal inequality there. Here you have constants that play around. And then a measure defined on the set that has the so-called doubling property. Measures are always increasing functions. So the measure of a ball of radius 2r is greater than the measure of a ball of radius r. Here you need some kind of a converse, and you have to have, of course, a constant for that to happen, and greater than 1. This is some kind of a regularity property for the measure. So this is what a space of homogeneous type is. It turns out that for us, the space of homogeneous type that works is given by the boundary of the domain as the supporting set. The quasi-metric turns out to be a suitable power of the absolute value of the denominator of the Cauchy-Leury kernel. And the doubling measure, look and behold, is the LLWeb measure. In order to prove that this function is a quasi-metric and this measure is doubling, one has to use the assumptions that we make on the domain, both in terms of regularity and the type of convexity that we work with. And this is the famous T of 1 theorem I was telling you about. We're not going to go into details. I just want to give you a flavor and a sense of what it entails. It entails estimates. You have to do lots and lots of estimates. You start with a space of homogeneous type, and then you identify a kernel defined on it. And you have to show that this kernel satisfies size estimates. As we said, the kernel has to be singular when W is equal to Z. It has to blow up. But it cannot blow up more than at a certain rate that you control. Number one. Number two, it has to have some additional regularity. Think of this as differentiability conditions if you could differentiate. Think of this as a difference quotient where what you're missing is a denominator which is lurking here. And then getting more technical, so this is the hypothesis on the kernel. Then you take the operator that's given by integration against this kernel, and it has to be relatively well behaved on a special family of functions that have lots of symmetries and certain regularity. Not only that, it has to satisfy certain cancellation conditions when you pick a special function, the function 1. And I'm not going to explain what this is, because for us this is going to be very simple. It's going to be 0, the simplest possible BMO function. Also the least interesting, but that leads to the simplest proof. So back to our setting, what kernel are we going to work with? We're going to work with 1 over the denominator of the Cauchy-Leury kernel. It turns out that this kernel has the properties you need to satisfy the Koifman's theorem that we had in the previous line. Right estimates with absolute equal to 1, weak boundedness, and as far as the cancellation conditions, here you use Cauchy formula. 1 is a particular holomorphic function, and so the Cauchy formula tells you that C of 1 is 1, not 0. So this means you actually have to modify the original operator a little bit to achieve this condition. A couple of words about the proof, and I will just talk about the modification that achieves this condition. So something that was crucial for us was the observation that if you take the Cauchy-Leury kernel and you take the kernel of its adjoint, each of them can be expressed as a derivative. Here by derivative I mean the differential of a form of degree 2n minus 2. Okay? Plus a remainder. Well, the remainder is going to be negligible. It gives rise to operators that are so regular we can ignore them. But this can't be any derivative, as we will see in the one-dimensional case. It has to be an appropriate derivative. And by appropriate, I mean that it has to have estimates. Estimates mean that you have to have some better homogeneity in the denominator. You see, this is the original denominator, very big exponent. Once you apply this differentiation, the exponent gets a little smaller. And so this kernel is a little easier to deal with than that. So once you have those properties, then when you compute the adjoint, we already know that C of 1 is 1, right? So then you compute the adjoint of C at 1. That's a function. It turns out to be a very good function, continuous up to the boundary. And in fact, even better than continuous, Lipschitz continuous, Holder continuous, so there's factor of class. Once you know that C star of 1 has this property, then it's very easy, it's straightforward or standard routine to modify the original operator by a quantity, another operator which is trivially bounded, so you don't have to worry about the regularity of this. But by effect in this modification, then the modified operator has the simple properties. So let's go back to one variable for a minute. A big business, this T of 1 theorem is an industry in harmonic analysis. T of 1 in BMO, T of 1 equal to 0, T of B in BMO for some other function. If you go back to the Calderon's result for the Lipschitz curve and try to prove it using a T of 1 theorem, it turns out you cannot do it by the special case we have here, T of 1 equal to 0. So it's interesting to revisit the original kernel and see what goes wrong when you try to affect that decomposition I was telling you about earlier. Well, it's very simple to express this kernel as a derivative. There you have it, and the remainder is trivial. So what's the problem? The problem is that although this is a derivative, it's not an appropriate derivative. It has not enough decay to get to do the estimates for the bump functions. That's where things go wrong. So although constructing a Cauchy-Leray kernel is a complicated affair, you have a little bit of a payoff when it comes to this stage. You actually get a simpler proof of the regularity result. So some further results. Let's go back to the original Euclidean surface measure, which was the object of interest for the classical harmonic analysts. What can we say about regularity with respect to that measure, sigma? It turns out that we're in a setting where you can also get positive answers. This is not by reproving the theorem, but rather by comparing the two measures. The measure we work with, the ad hoc measure, and the Euclidean standard surface measure. The two measures turn out to be equivalent, and the way to prove it is by realizing that the Leray-Levy measure actually encodes all of the analytical and geometrical properties. In particular, you can read off strong linear convexity by looking at the measure, and that gives you one inequality in the equivalence. And you also read off the regularity, C11, by looking again at this measure, and this gives you the other inequality. And in fact, it turns out that as soon as you reduce one of the two assumptions we make on the regularity or on the amount of convexity, you're in trouble. You can find counterexamples of strongly linearly convex domain in two complex variables whose regularity is slightly below C11, just C1 alpha, which have the property that the Cauchy-Leray integral for these operators, although well-defined, is not bounded in O2. Similarly, you can come up with examples of smooth domains that are only weakly linearly convex. They're going to have some flatness here, so that you can no longer separate them by hyperbola. There's going to be some flatness. And as soon as you do that, even if you build them to be infinity smooth, again, you lose the regularity. Some further results. Cauchy-Leray integral preserve spaces of good functions, Holder continuous functions, and you also have density results in the Hardy space in of some especially good functions. How much time do we have?
Just keep going.
5 minutes?
Yeah, yeah.
Okay.
We used up your time, so.
We started around noon, so let's keep it to 5.
Okay.
So here I'm trying to sell you an idea. And the idea is that harmonic analysts and complex analysts should become interested in what each of the other people group is doing. And good things can come out of that. So from the point of view of the harmonic analyst, people have been studying this Calderon-Zygmunt operator forever, for the past 40 years, and they're still doing so. It's a great field to work with. But here we're proposing to look at a special family of Calderon-Zygmunt operators, and those are the operators whose kernel is holomorphic, analytic, as a function of Z. Why should a harmonic analyst be interested in Calderon-Zygmunt kernels that happen to be holomorphic? And why should a complex analyst be interested in Calderon-Zygmunt operators to begin with? The answer is in the applications. It turns out that if you specialize to this particular kernel, not only Calderon-Zygmunt, but also holomorphic, such as the Cauchy-Leray kernel, you can use them to study operators that are far from being of Calderon-Zygmunt type, in particular orthogonal projections onto spaces of homomorphic functions. And I'm thinking Bergman space and Hardy space, for those of you that are familiar with this field. From the point of view of the complex analyst, the objects of interest are precisely the Bergman and the Hardy space, and they're reproducing kernels. From their perspective, the reason to be interested in Calderon-Zygmunt operators is because you can use them to study these orthogonal projections in settings where the known methods do not apply, kernel asymptotics being the traditional methods. This is domains that are not very smooth. So just to give you a sense of how do this orthogonal projection and holomorphic Calderon-Zygmunt operators come together, let's see if I can in 2 minutes sort of highlight this operator theoretic argument. So you're given a Calderon-Zygmunt singular integral operator, and if you're lucky enough, it also turns out to be a projection onto a space of homomorphic functions. Now for this to happen, you have to look at the kernel. And the kernel has to have two properties. It has to satisfy a Cauchy formula, reproducing holomorphic function just like Buckner-Martinelli did. But more than that, it also has to have the property that if you start from a boundary data, and you put, which is defined just on the boundary, and you put it into the kernel, and you compute the integral, the output will be a function of Z which happens to be homomorphic. This is what Buckner-Martinelli does not have, but Cauchy-Leray does. This is where it matters. So now what you have is two things. The Cauchy-Leray, your Calderon-Zygmunt holomorphic kernel, and your orthogonal projection kernel. And both of them happen to be projections onto the same space of holomorphic functions. So you then do as the operator theorists do, which is to say, compare them with one another. Two projections, one is orthogonal, the other is not. How do you compare two projections? By composing one with the other. And the fact that they're both projection onto the same space tells you that you have this identity. You take your Hilbert space L2, apply T, you project onto the subspace. You apply P, that's the identity of that subspace, and so you recover it. You switch the order, same reasoning. Now you take the second equation, and you take adjoints. Here you use the fact that the projection is orthogonal. Orthogonality is equivalent to being self-adjoint. So now you have this third equation. Equation 3, equation 1, subtract 1 from 3, you get this equation. And now you solve for the Calderon-Zygmunt projection, you get this identity. And I here is the identity operator. Okay? Now you exploit the symmetry of the operator that's obtained by making the difference of T and its adjoint. There's nothing special about T here. What's special is that we're subtracting off its adjoint. So if you take the adjoint of this difference, you recover the original operator except for a sign. Skew symmetric. As a consequence of skew symmetry, one can show that the identity minus the skew symmetric operator happens to be invertible on this very special space. And so what do you have now? You're able to invert this operator here, and so the new equation is going to look like this. This is a great equation because you have completely separated the orthogonal projection from the other operator. On the right-hand side, you just have p. On the left-hand side, you just have things that have to do with t. This is an identity that holds in L2 where everything makes sense. The problem with orthogonal projections is that they're not explicit. So they're naturally bounded in L2, but there's nothing you can say by just looking at them about their behavior in LP for p other than 2. That's not the case for Calderon-Zygmunt operator. You have to sweat like a pig to prove L2 regularity, TO1 theorem. But once you know that they're regular in L2, you get regularity in LP for everything. Now what you have on your left-hand side is one piece of an object that's regular in LP for everything. And so the challenge is to see when is this invertible operator actually bounded also in LP for p other than 2, as opposed to just 2. And this is a problem that has been studied a lot. It has been studied a lot, and you will not be surprised when I'll tell you that the answer again depends by the amount of geometry and the amount of regularity that you're assuming on your domain. But answers are known in many different contexts. Originally, for domains that were infinity smooth and strongly pseudoconvex, and results pertain both to the Lego projection for the Hardy space and the Bergman projection for the Bergman space. More recently, we have been able to reduce the regularity from C infinity to C2. This is what I was referring to earlier on. And there is a lot of work to be done. New kernels have been identified very recently by Steve Kranz and Michael Grandier. So these are kernels where one has a lot of regularity, kernels for domains, Calderon-Zygmunt type kernels for domains for which one has a lot of regularity, but little convexity. Flatness is allowed. And there is a lot of work to be done here because we don't know whether these holomorphic kernels are regular bounded operators in LP. And we don't know whether the orthogonal projections for the Hardy and Bergman spaces of this operator are bounded or not. So lots of work. So this concludes the content of my talk. If any of you is interested in reading some of our preprints and earlier paper, I'm happy to provide references. And thank you very much. Other questions?
I guess the more interesting case for this orthogonal projection is when p is less than 2.
When p is less than 2. Yes, and in fact it turns out that precisely because the projection is orthogonal, if it is bounded in an interval about p equal to 2, the interval has to be symmetric. So, if you can manage to show that it's bounded in a p for p between 1 and 2, that's all you need to do. Because then by self-adjointism, you recover p between 2 and 4. So you're right, the enemy is only a one-sided interval. That's the most difficult case.
For the part that you didn't talk about, what you mentioned in the first part of your talk, was this Calderon-Zygmunt theory. If you have the elliptic PDE in the divergence form, for instance, and the coefficients are, let's say, L infinity, then we know that the W1P theory is by Myers. So you have existence for P around 2.
Yes.
Right. Can we extend that? Is it possible to extend that, or that's it?
So on what kind of domains are you looking?
Lipschitz.
In a Lipschitz domain. So you only have the theory for p between...
For p between 2 minus epsilon and 2 plus epsilon.
I believe that this kind of questions have been studied by Koenig and his collaborators, and they're able to characterize epsilon in terms of the Lipschitz constant of the domain. So you have 2 minus epsilon of b and 2 plus epsilon of d, and there should be examples that show that the size of the interval is optimal. Meaning, if you take a Q that's outside of that interval, you can find a Lipschitz domain whose constant is given by the constant of the interval you'll be looking at, for which there is failure of a Q regularity for Q regularity for Q in there. So you can have examples of Lipschitz domains for which you have a larger interval, but if you look at the entire category of Lipschitz domains, you're bound to have a counterexample. In this type of situations, usually looking at wedges help. So for convex wedges, you usually can recover a large interval, p between 1 and 3. But if you look at convex wedges, you can recover its counterexamples. That's where I would be looking at too.
Other questions? Thank you again.